Hello students. In this video we'll discuss rules for counting significant figures. All measurements have a degree of uncertainty associated with them. For example, a DNA test is 99.9% accurate. It's not 100% accurate because it is a measurement, and therefore it has some degree of uncertainty associated with it. Significant figures, which I will probably refer to as Sig Figs, also known as significant digits, are the numbers we obtain from measurement, and they determine the precision of the measurement that is made. Significant figures in a measurement include all of the known digits, and those digits are certain, plus one estimated digit, which is uncertain, and is typically the last digit in the measurement. So how do we obtain significant figures? Again, we obtain them from measurement. So let's say we take the length of something and we find that that length is, this is 12 right here, so we go 1, 2, 3, 4, 5, 6, 7, 8, so it's 12.8 centimeters. But notice that the arrow is just past 12.8 centimeters, but not quite at 12.9 centimeters. So we have to guess or estimate where this arrow lies between 0.8 and 0.9. So I would estimate it to be 5. So we would say the measurement we estimate with the last digit of uncertainty is 12.85 centimeters. So this last digit, this 5 here, is an estimated value. And anytime you take measurements, you're going to get significant figures. So we have to have rules for counting significant figures. Okay, so let's run through these. First rule says that all non-zero digits 1 through 9 are always significant. So 25,643, I would count 1, 2, 3, 4, 5 Sig Figs. Second rule says that all captive zeros are always significant. So think of a captive zero as a zero being sandwiched between two non-zero numbers. Okay, so in this case 600,012, I would count 1, 2, 3, 4, 5, 6 Sig Figs here. All of these zeros are captive zeros. Alright. Rule number 3 says that all leading zeros are not significant. So these are leading zeros here. And leading zeros are not significant. They just act as mere placeholders. So we won't count these. So in this particular case, we have 1, 2 Sig Figs. Rule number 4 says that all trailing zeros after the decimal point and preceded by a non-zero number are significant. So here's a situation. This is a trailing zero. It comes after the decimal point. It is preceded by a non-zero number. Therefore, it is significant, making this zero a captive zero, and therefore it is significant. This is a leading zero, and remember, leading zeros are not significant. So in this case, I would count 1, 2, 3, 4 Sig Figs here. And rule number 5, all trailing zeros not terminated with a decimal point or come after a decimal point are not significant. So here's a situation like that. These are trailing zeros. They're not terminated by a decimal point, nor do they come after the decimal point. So therefore, these zeros are not significant. So I would count 1, 2, 3, 4 Sig Figs here. Okay? Here's a subtle difference between these two, how these two are reported. So 511,000, terminated with the decimal point, makes this zero significant and consequently these zeros significant. So I will count 1, 2, 3, 4, 5, 6, 7 Sig Figs here. It's a subtle difference that you need to be aware of. If that zero is terminated by a decimal point, it becomes significant. If it's not terminated by a decimal point, it is not significant. This is the case for trailing zeros, okay? The next thing I want to talk about is rule number 6. Really what this says is that when you have exact numbers, and you get exact numbers from counting or from definitions or from constants. For example, exactly 1 hour is equal to exactly 60 minutes. Exactly 12 inches is in exactly 1 foot. So, or exactly 1.609 kilometers is equal to exactly 1 mile. And typically we use these in conversion factors. These have infinite number of sig figs, and when you calculate using conversion factors, what you have to remember is that you're only as precise as your least precise measurement. But because these have unlimited number of sig figs, we cannot use these when we try to determine the proper number of sig figs in which we should report our answer. More of that to come when we talk about dimensional analysis. So let's look at some examples here. Let's count some sig figs. Alright. So in the first example, I have 0.0065. The zeros that are coming first are leading zeros. Therefore, they are not significant, so I'd count 1, 2 sig figs. In the second case, I have 100.020. Okay. So these zeros are captive zeros. They're sandwiched between two non-zero numbers. This zero is a trailing zero. It comes after the decimal point and is preceded by a non-zero number. So I would count 1, 2, 3, 4, 5, 6 sig figs here. This 2,500. It's not terminated by a decimal point, therefore these trailing zeros are not significant, so I'd count 1, 2 sig figs here. Here's a case where we have a number reported in what we call scientific notation, 7.90 times 10 to the negative 3. Whenever you're counting sig figs, focus on the coefficient. Don't worry about this. You want to focus on the coefficient. This is your coefficient. So this is a trailing zero. It comes after the decimal point. It's preceded by a non-zero number, so it is significant. So I would count 1, 2, 3 sig figs here. In this case, 670.0. This zero comes after the decimal point. It's preceded by a non-zero number, so therefore it is significant, making this zero significant now because it is a captive zero. So I would count 1, 2, 3, 4 sig figs here. Leading zeros here in 0.00001, right? These are leading zeros, and we said that leading zeros are not significant, so I'd count 1 sig fig right here. 18.84, all of these are non-zero digits, so therefore all of these digits are significant, so I'd count 1, 2, 3, 4 sig figs right here. This is 2,500, capped off with a decimal point at the end. That makes this zero significant, which consequently makes this zero significant, so I'd count 1, 2, 3, 4 sig figs here. So I hope this video was helpful to you, and happy studies.